Thank you. Good morning, everybody. Thank you for coming to our presentation. My name is Romain Trachel, and this is Alex.
Yes, hi, I'm Alexandre Perrault. Thanks for being here this morning.
We are very excited to be here. We are from IDOS. We are both machine learning specialists. IDOS Sherbrooke is a sister studio of IDOS Montreal in Quebec, Canada. We are doing research and development. We are not. This is not actual production presentation. This is an R&D project. We are both holding a PhD. Alex has a PhD in pure maths, and I'm in machine learning and neuroscience. So we're trying to be not as technical and scientific to let you understand what we have done. I'm going to give you a general overview of the presentation to give you a key concept about what we did, and then I'm going to leave the mic to Alex to let him present more details about the project. So I'd like to start with an iconic game. You probably know Pac-Man. That's a game where you're playing the palette here. You have to collect all the coins while being chased by the four ghosts. This is a unique game where each ghost has his own personality and his own chasing behavior. And the game is really engaging in part because it's constantly alternating between the chase mode and the scatter mode, where the ghosts are moving to the four corners of the map. So these two modes are alternating at regular interval. I think it's 20 seconds for chase mode, then 7 seconds for scatter mode. Then it goes back to chase mode. And that's varying as a function of the level. When you complete all the palettes, you go to the next level. And so that's a unique behavior that gives some room to the player. You know, you've been passing through intense chase period, and then you have a bit of breath, the ghost goes away. And that's what I found very unique in this game, and that was a good inspiration for us. How can we balance like that intense, difficult period of time with some relief to give some room to the player. And I don't know if you're familiar with game AI tools like this one called Behavior Tree. Pac-Man was not implemented with Behavior Tree, but for the sake of the presentation, I would like to give you an introduction, an example about what kind of, how we could implement the ghost behavior with Behavior Tree. For instance, here we have Blinky, the red ghost, and the way you read Behavior Tree is you start from the root and you go down to the leaves by evaluating the node from the leftward node to the rightward node. And here, for instance, the way you would read it is you will have this selector node that's going to say, well, if we are in scatter mode, then Blinky needs to go to the scatter location, to the corner of the map. If we're in chase mode, it's going to go straight ahead to the player location. So like that, Blinky is always chasing straight ahead to Pac-Man. We have another ghost. I think there were. No, that's fine. Pinky. Pinky is going to be always chasing past Pac-Man one tile ahead when he's in chase mode. So we don't change much the behavior tree with respect to the previous ghost. It's just that instead of chasing Pac-Man straight ahead, it's going to go one tile, two tiles ahead of Pac-Man. And like that, you could implement another behavior tree, a slightly more complex behavior tree for implementing Inky, the blue ghost, who's basically is going to be always roaming around Pac-Man, but not always chasing him directly. There is this condition where if he's close to Blinky, he's going to go ahead of Pac-Man. Otherwise, he's going to go to this a bit weird target location where you have to draw a line between Blinky, Pac-Man, and then he's going to go to this location. So that makes Inky pretty aggressive when he's close to Blinky, and otherwise he's like roaming away close to Pac-Man. And the last ghost, Clyde, who's a bit the schizophrenic ghost, because what he's doing is that when he's far from the player, he's going to go straight ahead, like Blinky, straight away to Pac-Man. And when he's approaching Pac-Man, he's going to like change his mind and go to the scatter location, to a corner of the map. So it made this ghost a bit unpredictable. He's sometimes chasing Pac-Man, sometimes doing his own thing. So you see that the complexity of the behavior tree can, in this simple example, can be a bit scaling. You can imagine how more complex behavior could be implemented and how you can have very large and wide behavior tree. So to tackle that, Unreal has an experimental AI tool called the environment query system. And in this example of Pac-Man, you would be able to have a single behavior tree for implementing the 4 chasing behaviors that I presented earlier. By doing that, you will have a box which is called an EQS query that will send tests to each tile of the game, asking simple tests, whether like I'm far away from Pac-Man, I'm close from Pac-Man, and so on and so forth. So like that, you have a single behavior tree. You of course need to implement 4 query types for each of the ghosts, but you see a bit where I'm going, that you can refactor everything and have just one single behavior tree for all your behaviors. And going a bit deeper on that, to refactor and to having generic tool, machine learning can be also very powerful to to predict variable like game difficulty. When you think about that, game difficulty is something very subjective. You have also the easy, medium, hard mode that you find in video game, but that's like hard coded. And what I'm talking about is really how you feel the difficulty in the game. And a simple example could say, yeah, we could take the distance between the ghost and the player and take 2 observations. For training machine learning model, you need observation, you need data. And those 2 points, for instance, correspond to this gameplay situation where you have Pac-Man surrounded by the ghost, they are close, the difficulty is probably high. If we take another example, an opposite one, where Pac-Man is located here and is pretty far away from the ghost, you could train a machine learning model, and what you will do with these 2 simple examples is something that we probably all know is linear interpolation. Okay, and if you take, the goal is to use this machine learning model on new observation like this one, where you could probably be here, and you kind of get that the model is a bit off the line. It's with 2 points, you cannot do really many things. What you would like to do, ideally, is collect many observations and end up with a nice model like that is really describing what you collect. And of course, this is a very simple example. The real power of machine learning is when you have several variables, multi-dimensional variable, like we could have 3D, 4D, ND data. That's just an example it's harder to visualize. But in principle, yeah, you will have the mode of the game, the number of palettes that's been collected, the time, etc., to better refine your model. And why we are doing that is because we want to have engaging video game experiences, right? If you look at this figure, it's from a famous game designer. I think he worked on the Flow game. And what he's claiming is that if you look at the player experience, so each dot here corresponds to a game, like you're playing 1 level, then level 2, then level 3. And what you want is to balance the game difficulty according to the player level. And you want the game to be not too hard, not too easy, to engage the player into a flow mode. And that's what we want to do, is to use machine learning in conjunction with game AI to detect game difficulty and to adapt the game from level to level to maintain the player into a flow zone. And that's something that is also subjective and varying. From novice player probably have their flow zone a bit lower, expert player will have their flow zone a bit higher. That's something that varies from player to player, so that's why machine learning approaches are very good, because you can feed data onto the actual player data. So it will be personalized based on your own experience. So yeah, that leads me to the project overview. As I said, the goal is to combine game AI with machine learning for having a better fine-grained control of game difficulties. This is quite challenging because those 2 schools, machine learning and game AI, are a bit separated from each other. Here, what we want to do is really take game AI tools to get all the know-how tools from the community, the dev community, and also the players. They are used to this kind of stereotypical behavior. But we want to include some machine learning to have a better personalization of the game AI tool. And the methodology that we had is that we developed a small game. We started from the top-down template of Unreal 4, and we actually collected some data, trained model, and play-test it with actual human players. The aim of the game is to collect 16 orbs that are scattered on a map while being chased by an enemy character. So it's really like Pac-Man, but point and click and on a 2D map. And the tool that we use is behavior tree and EQS for setting the patrol location of the enemy. So the enemy is patrolling in the map. I will show a video just after. The enemy is patrolling in the map, and when he sees the player on line of sight, he's going to chase him. And we use machine learning to predict when the player is going to be captured by the enemy, and modulating the patrol location to have a certain location where the enemy is sent to really kill the player, and having some other patrol location where we want to be more in an easy mode, where we could send the enemy to a location that is less dangerous for the player. So this is a video of the 2D game, the top-down game. You will see on the top left corner a mini-map. You see in blue the player. In green, we're going to have the orbs that the player has to collect. Here we see the mouse cursor, so the player is pointing, the character is going to move there. And yeah, here is voilà, how it does. The enemy is going to appear in red in the map. You see it here, and it's like constantly patrolling. The player is controlled by a real human player, and you see that he's hiding behind the pillars to don't get spotted by the enemy. So the enemy is still patrolling, and then he's going to enter line of sight and run towards the player like that. So here we have actual subjective report asking the player how he felt. The game was easy, medium, or hard. And so again, underneath we have a behavior tree. We have the EQS system that is used to send the enemy to specific patrol location. We see here debug mode of the EQS system, and here the behavior tree that is running. So here is the selected patrol location. This selected particular patrol location was decided by a machine learning model. We do an inference, and based on the result, we decide to send the enemy to this particular location. Okay, and so those kind of subjective report, we use it to really understand how the player was feeling the game. You can imagine that in an actual real game, you cannot poke the player every, like, say, 5 minutes. How do you feel the game? Was it fun? Was it easy? Was it medium? The goal is to replace this kind of measurement with machine learning, such that we can do it seamlessly while the player is doing. We can know how he was feeling the game. And yeah, with that, I'm going to leave the mic to Alex, who's going to present more detail about it.
Thanks a lot, Romain. So yeah, I want to explain more in detail the little video that we saw and how we actually implemented this with machine learning and EQS. So I want to start off by describing a bit EQS. It's a tool that allows you to do spatial reasoning in Unreal. This is a screenshot of a simple EQS blueprint taken from the Unreal documentation. And how it works is you can generate points around the map on which you want to perform spatial queries. And then in blue, you have sets of tests that you can perform. And these are considerations such as line of sight or distances. So you might want to know, is a point going to allow the character to be at a point where they have visibility on the player, or is this point close or near to certain interest points? I will show visually the debug tool that was also shown in the video for the simple EQS test. In blue, those are points that are set to 0, and this is because they failed the visibility condition. So these points do not have visibility with the player because there's a pillar that the player can use to hide. So these points are discarded, and then from blue to yellowish colors, from green to yellowish colors are valid points because there is visibility, but they're ranked according to the distance. So you can set these tests to either be Booleans that set points to be valid and invalid, or simply having a score that tells you which one satisfies more a condition that you care about. You use these EQS systems within behavior trees, and this is kind of where we started our exploration. So this is, again, a behavior tree that is taken from the Unreal documentation, and which implements a simple patrolling and chasing behavior, as we saw in the video. And we were wondering how we can make this simple behavior tree more engaging and start using EQS and machine learning within this simple framework and have a gradient of difficulty. So to go quickly over this behavior tree, what it does is it has two modes. So there is the chase and the patrol mode. We'll actually start from the right side, the patrol mode. When the character is patrolling around the map trying to catch the player, in this simple implementation, it just finds a random point on the map and patrols there. And then they wait, and then they move again to the following random patrol location until eventually they break into line of sight with the player, and then they fall into the chasing behavior on the left. And this is simply, as soon as there's line of sight, they start running directly towards the player. So the next step is how can you use EQS to make this random patrolling system a bit more engaging and interesting? So on the left here, we designed a very simple EQS system that could be more difficult and more engaging for the player potentially. It's also very aggressive, so we'll get to later on how we can modulate these levels of difficulties, but just for the sake of seeing how one could use these EQS systems to generate more engaging difficulty levels. Here we set an EQS system that looks for points on the map where there is visibility on the player, so the enemy is likely, when they go there, to enter in line of sight and be able to chase the player. And we also chose points that are very close to the player. So this is, again, very, very difficult game mode because the enemy, even when they're patrolling, is always going to points that are at that moment very close to the player and will lead to visible, points where there's visibility to the player. And once again, the left branch of the chase is untouched, and only the right patrolling location is modified, where the find random point on the map has been replaced by returning the point chosen by the EQS query. So as I was saying, we have these two modes. One is very simple. It's this random patrolling location, which is very easy to dodge around because once you see where the enemy is running towards, you can kind of run the other direction, and unless they're extremely lucky, you'll get away with it. And then we also showed this very simple but difficult EQS system, but it becomes very tricky once you want to have, you obviously don't want a system that's insanely difficult and the enemy is always going towards you. As Romain was saying with the example of Pac-Man, if you want a more intermediate or more engaging level of difficulty, you might end up having to stack up many different considerations and have various different EQS systems for an easy mode or for a hard mode. And you can see here, for instance, you can have considerations on like the angle between the directions that each character is going towards, the distances, the visibilities. Like there's many considerations that you can have. And this is something that machine learning is very good at, is having many variables and considerations that are of interest and learning in a purely data-driven way how to combine them together. So we were thinking, is there room for machine learning to simplify, or at least to be an alternative to designing these handcrafted EQS systems and simply learn from the data to generate these and also have control over whether we want the system to be easier or more difficult. And I'll get into that. Since the machine learning model allows you to output a value of likeliness of capture, for instance, you can really threshold the output and have one single EQS that will also handle the various difficulty levels. But I'll get there in a second. So before training any machine learning model, obviously what you need is data. So we automated a gameplay with bots so that we would be able to collect many data, because it can become time consuming to have many players play this game to collect data. Obviously, that would be the preferred solution, but for our prototype demo, it was good enough to simply automate a simple bot to collect this data. So the bot follows a very simple strategy as a player. It goes to collect the orbs around the map, which is the aim of the goal. And whenever the player enters line of sight with the enemy character, the bot simply will hide behind a pillar and break the line of sight. And after some seconds that you manage to break the line of sight with the enemy character, the enemy character will start patrolling again, so then you're good and you can go around picking up orbs. So it's not so different from how a player would play, but it's what we implemented to have an automated data collection pipeline. And the data that we collect is at regular time intervals. It's important that you keep regular time intervals to keep the temporal coherence of the game and of the dynamic of the game. We collect information such as the positions, the directions of the characters, information about the orbs, and various such game state considerations. So we get kind of a snapshot of what does the game look like at this moment. And this is what will go as inputs to our machine learning model. So we use a neural network to input all of this data that we have. Once we collected, I think it was around 400 simulations. We just had all these data of every, like 3 times per second, we're collecting this information. And as input, we had this snapshot that I just showed. And as an output of the model, what we're trying to predict is how much time is, how much game time essentially is remaining, like how long before the enemy actually manages to capture the player. And this is what we ended up using for, once we know this time or this expected time before there's a capture, we can decide how much room, how much life expectancy kind of do we want to give to the player before they get captured, and use that as an output of our EQS system and then feed it to the behavior tree. So I explained a bit in detail the snapshots. So this is the inputs of the model. As an output, this is kind of in a purely signal fashion what it will look like. I will show a replay of the minimap afterwards with these predictions. It will be maybe more clear then, but before showing that video, I quickly wanted to understand what the predictions were, because it's not just a value of, are you being captured? You really want to propagate backwards in time information about the couple of seconds before you were captured. So this is very common in these types of machine learning problems where you want to learn these very rare signals. So you have, in the x-axis is just the time, so time steps during the game, and in the y-axis in green is the actual, the spike, the top of the spike is the actual moment where players were captured, and then it decays exponentially backwards in time to keep some trace in the short-term memory of we were about to be captured. And in blue is what the machine learning model tries to learn. Well, it's the actual predictions of the model, which should match to some extent the actual values in green that were observed. They don't match 100%, and this is very normal. As we will see in the video in a second, it can happen that there are positions where there's like threat, or you're very close to the enemy and the model spikes up, but actually the player managed to get away, and things of the sort. So here is the video. We have the minimap that will play as earlier in the video that Romain showed. In blue is the player, and red is the chasing enemy character. And on the left-hand side will be the true values. So these will start very close to 0, and they will slowly start shooting upwards as a capture event is about to happen. And on the right-hand side is the output predicted values of our model, which should similarly correlate as we're getting closer to a capture event. The machine learning prediction goes up. So here it goes. So as you can see, the model starts off quite low as we're running around and doing our thing. And then as soon as there is a capture, the predicted values go up. They don't necessarily, once again, match with the leftmost values because in truth, it happens often that the player manages to escape even though they were close. Or vice versa, it can happen that you were very far off and then very suddenly there is a capture. But here's an interesting moment where the model really spikes up and you can see that there was indeed a very tense situation between chase of the enemy and the player. And eventually the player manages to get out of trouble and get away. And so this is the kind of situations where even though the predictions don't match the true values, it was very fun for us to see that the model was indeed capturing the kind of danger and intense chase moments that we were wanting to capture. Here's again another example of the model being very confident that there is danger nearby, but the actual data of the replay shows that the player manages to escape. So how do we use these machine learning models with EQS? So what we do is we have our grid. So this is the same debug tool that we showed earlier. And what we do in a game snapshot such as this one is we keep all of the game variables the same. So we're imagining that we're in this game state, and we artificially remove the enemy in red, the chasing character, their position and their direction, and we replace it with what if at each of these points that are being queried, the character were to move in that direction to that point and artificially modify the enemy position to be each of these orb points on the map with corresponding new direction. And then we feed these inputs to our machine learning model, and we ask the model what would be the likelihood that the player will be captured in a second, in 2 seconds, in 3 seconds. We can kind of poke the distance and time that we're interested in these capture events from happening. And the resulting values are what is being showed on the map. So as you can see here, the very bright green spots are very close to the player, like in the direction of where the enemy would go towards if they were walking towards the player, so it makes sense. And in red, we're going completely in the opposite direction of where the player character is moving towards at this moment. So it's reassuring to see that the points seem to make sense intuitively. So as I was saying, our point is not to have super aggressive bots that can simply just learn to always go to the maximal difficulty level positions. Like, this is not our intent. It's not to have the best unbeatable bots possible. Our idea was really to have intuitive and understandable description of difficulty and have very precise inputs of what the machine learning model outputs that can be used to modulate game difficulty. So you don't need to choose points of the model that says we are about to capture the player in less than a second. You can tell the model to choose points where you are 1, 2, 3, 4, 5 seconds away from capturing the player. And this is the fine-tuning lever that we used to modulate the game difficulty. So we've chosen this fashion 3 difficulty modes. The easy mode, we simply chose take the point which is the least likely of leading to a player capture. So a bit similar to the scatter mode in Pac-Man. It's really just go at the opposite end of the map and give the player some breathing room. This is fine. The medium mode is an in-between. So this is, we selected 6 seconds. We tried with different values, but 6 seconds seemed to be a good spot of difficulty that was a bit in between. And you can see that the map is a bit more green in an area that's the player is moving towards the left, and all that left area is a bit more green than in the more aggressive mode, which I'll describe in a second, which we already saw before. So it still has points that can be very close to the player, but the general area that the machine learning model selects is a bit more wide, and often it doesn't select points that are so close to the player, but that are a bit more kind of like, I forgot which ghost it was that was going 2 tiles ahead of Pac-Man, but like you can imagine, like instead of going directly to the player, it's kind of going a couple of seconds in the direction where the enemy is going. So yeah, then we'll show a bit some of our results. So as Romain said, we tested with some play testers these difficulty modes, and we're curious to see, okay, well, like in a purely data way, we have these numbers, but do players actually notice a different level of engagement with the different game modes? So we tested three patrolling EQS systems for patrolling. The left branch, as I showed before, always remains the same. So when the enemy character enters in line of sight with the player, they will start chasing them. However, the right branch, the patrolling one, will change. The EQS patrol point will be different. And we asked participants to rate the difficulty level for each of their experiences. So that was the little UI that Romain showed in the video before, where players could say, this felt pretty easy, this felt medium or hard. And finally, we didn't want only subjective reports, but we also wanted to track how much scoring could players actually obtain with each mode, and how long actually before they were captured, like for how long were they able to play the game before they were captured, which would be a bit more of a data and objective, let's say, difficulty mode. So we have these subjective reports and these objective heuristic metrics for how actually difficult was the game. So these are kind of the results that we obtained from our experiments. So first we tested the random patrol versus what we call EQS hard, is our machine learning model based EQS system that always selects the most difficult, or the point with likeliest player capture. And EQS line of sight is the first EQS that I showed that was selecting points that are near and with visibility to the players. So as we could have expected, the random patrolling behavior is the easiest mode, where players were reporting the most that they felt the game was very easy, and they were succeeding to complete the level very often. 16 is the total number of orbs on the map. So you can see that in the left column, this one, for the random patrol, it was very often players were finishing the game or very close to finishing the game, whereas it was very rare events in both the machine learning difficult mode and the line of sight based EQS system. They're both pretty comparable. The scoring is slightly lower for the machine learning model based one, but the difference is rather insignificant. So we're very happy to see that our model was able to be essentially equally as difficult in the hard setting as a very aggressive EQS system that was directly being fed the visibility and the positions of the players at this instant. And similarly, in terms of gameplay duration, we can see that in the random patrol, the game would last much longer than both for the machine learning difficult mode and the aggressive line of sight based EQS system. We then compared the three machine learning based EQS systems with the thresholds that we described earlier. So easy being we're sending the enemy character at points that are not very likely to result in a capture event. Medium being capture happening in the next 6 seconds, and the hard mode being once again the most likely capture positions. And once again, we can see that there's a nice gradient of difficulty we're in the easy mode once again. Players were, I think the average was like 15 orbs per game. So very, very high, very high chance of completing the game, and not very difficult at all. In the medium case, it was a bit more in between. And finally, for the hard system, the game would shoot back down with lower scores and lower game times. So we have this nice gradient of difficulty that was exactly what we wanted to achieve. So we were pretty happy to see that. And also in terms of reporting, the players were reporting easier to harder sensations of difficulty with both of these, with the 3 game modes. So I will slowly start wrapping up. So we have many other research directions that we were interested in. This was a first prototype that was encouraging for us to kind of pursue these prototyping ideas. One thing is the system does not need to predict a capture event or a game over event. It can be very general. At the end of the day, we're only predicting game events from happening in the game. So these could be pickups, like is a player about to collect some items on the map, or questing, or is a player likely to use an ability, and all these kinds of dynamics that one can try to feed a machine learning model this data with, and then use these predictions in your systems. We tested, for instance, the item pickup predictions. We thought it might be interesting to have a bot that would try to defend different items on the map at various locations. It was less convincing because it would lead to a bit more boring gameplay where the bot was just very defensive and roaming around certain regions of the map to always defend orbs that would end up never being collectible. But we still thought that it might be interesting to come up with a fun idea or a fun way to incorporate these types of predictions in this behavior tree system. And another idea that we have is using machine learning with EQS for spawning. So for instance, if we're interested for questing or for, should we spawn a certain weapon or certain item on the map, if we can use these predictions of how likely is a player to perform a certain action or to interact with something, then we could spawn events on the map or items on the map or even a quest. So these are all ideas that we find very interesting and we're hoping to tackle in the future. So the main takeaways for us is that machine learning is very powerful for being fully data-driven and squashing a complex EQS test into one. It allows to reduce the number of handcrafted rules and to have just one system for many difficulty levels. However, you lose time, like you gain maybe time on this front, but you also need to spend a lot of time collecting data and being very careful with how you collect your data, how you process it. If you have game changes, you need to recollect your data, etc., and model training. So there's always a give and take on these two fronts. And yeah, the machine learning predictions can be used with one model to be flexible in these difficulty goals. And we're very excited because for us, this is a first, well, in our experimentations, we're trying to go towards a hybridization of machine learning and game AI tools. So we definitely don't want to build very purely controlled reinforcement learning agents. We really are interested more in how we can use these very interpretable game AI tools and understand very well where pieces of machine learning predictions can influence these behavior trees or other game AI tools in a way that you can really have discussions with a designer and be being very clear what the machine learning model is predicting and still incorporating all these very great game AI tools that exist. So that will be it for me. Thanks everyone for being here so early in the morning, and we'll take questions.